Hi everyone. So this is going to be a review for what you learned in applied research already. So if you feel like you have a pretty good handle on that, I'm going to say you don't have to watch this video. Otherwise, I'm going to go through that same information, but just go through it more quickly for a quick review. But this is what you will be expected to know walking in the door of the intensive. I would like for you to be able to say, hey, that's positively skewed. I'd like you to be able to say, that's platykurtic. Be able to calculate the mean and sample variance, sample standard deviations, and understand what nominal ordinal ratio and interval data are. So here is the acronym NOIR, like night in French. Okay, so this is the acronym I learned in college when learning all of this. So remember nominal data? This is measuring basically categories, the different buckets of things. We can have males and females, different grade levels, different groups, different types of dogs, different types of teachers, okay? So sometimes you might put continuous data into categorical variables, like you might say those in the age group of 18 to 30 is in one category, okay? So that's something to think about with data, but that's nominal data. Now, ordinal data has to do with ranked categories. Something that's interesting here, Likert scale survey items are typically ordinal data because you can't really say there is an equal distance between strongly agree and agree as there is between agree and neutral. So with this type of data, there are not equal intervals between the number. So for example, between first place and second place, like if you're running a race, there may be a 10-second difference, but between second place and third place, there may be a 40-second difference. So the intervals are not equal. I will say this, you will watch in a JMP video later that Likert scale in JMP can be coded as continuous later. I just want to go on and tell you that. But officially, Likert scale data is ordinal data. Now, interval data is when there's no true 0 point and you can't really do multiplication with it. So like with IQ scores, if someone's IQ is 100, you can't really say they're twice as smart as someone with an IQ of 50. Usually most of our scores are in testing are interval data, because it doesn't mean that if you have a score of 0 in intelligence that you have no intelligence. Ratio data, however, really means that there is a true 0 point, and I like to think of that with the 0 in ratio. So like if you have 0 absences, that really means you were not there. There were 0 absences. If you made 0 money in your salary, that means indeed you made no money. Multiplication does work here. We can say someone made twice as much as someone else, okay? So what I'd like you to know also is that interval data and ratio data together are called continuous data. The numbers go up and the numbers go down, and there are intervals between the data. Okay. All right, to find the mean, you add the observations up and you divide by the number of observations there are. I would like to point this out as review. If you see Greek numbers, that has to do with the population. If you see regular letters, I said Greek numbers, Greek letters. Greek letters are population. Regular letters are samples. And this little sigma sign means sum of, S-U-M. So we add numbers together and we divide by the number of numbers there are. Okay? All right. So hopefully you know how to do that. Let's talk about median. Median has to do with the middle score. So it's really so very easy. You would put all these numbers together and literally find the middle number. Now, with salary, like let's say the median is $50,000. Median also means that 50% of score, 50% of all the observations of salaries would be below 50,000, and 50% of all the population of salaries would be above 50,000. Okay, so that's another thing median tells us, is considered the second quartile of scores. Now, what if there are even numbers here and you literally figure out which one is the middle number here by crossing them out and figuring that out? But if it's even, you would take the mean between the two middle numbers. Mode is the most frequently occurring number. Sometimes you could have two modes, all right? But here, the mode would be 23. So here, the mode is 19 and 23. So this is considered bimodal. And so you can see how there's different ways that in a distribution that these would look. Here we have two prominent modes. There's more here than this one. Here we have a mode number would be. All right. You can also have mode for nominal data. So if you have participants from 12 different nations and most of them are from Canada, the mode would be Canada. Let's talk about a distribution of scores. This shows that if you have a sample of data, and most of the time is probably going to be a normal distribution of scores, or fairly normal, because that is the way the world works mathematically. It's really awesome. But at times there will be some things that are positively skewed or negatively skewed. So we may see more observations on the high end or more observations on the low end. Now this used to totally confuse me, because like in my head it would make more sense for this to be negatively skewed because there's more people down here. But that's not the way it works. Remember the trick? The skew is in the skinny. The skew is in the skinny. So if we were looking at test scores in a negatively skewed distribution, if the test was way too easy, more kids would score really high and less kids would score low. So this would be a negatively skewed distribution. If the test was so very, very hard, most kids did not do well at all, and few kids did well, they scored highly, that's a positive skew. Now, when looking at this, when the mean is higher than the median, it would be a positively skewed distribution. Okay, so how could we think about this? Think about your neighborhood. And think about in your neighborhood, like maybe most houses are, I don't know, $150,000. So they're depending on where you live, maybe they're just medium-sized houses. But you have this one huge mansion in your neighborhood. So that pulls the mean to be higher than the median. And so in that case, you have more houses that are pretty medium-sized and fewer houses that are like these rich mansions, okay? So that would show a positively skewed distribution because you have less number of houses in the high end and more houses kind of in the medium area of like $150,000. I'm totally making this up. All right. So let's think about negatively skewed distributions. So this might have to do with retirement ages. Like a lot of people retire late in life, but let's say you have a few people, like maybe from the military or something, that retire super early. And so they might pull, so the mean score is less than the mean age at retirement is less than the median age, okay? It's because they're younger, so they're lower, they have lower age here. So this would be an example of a negatively skewed distribution. So I often refer to this because sometimes that's tricky to me, thinking, okay, if the mean is higher than the median, what is it again? Is it positively skewed? And then, so this, I really like this picture to show the relationship between mode, median, and mean. All right, quick check. Check yourself. What type of distribution is this? Positively skewed or negatively skewed? All right, so if you've said positively skewed, you are correct. So we have a lot of people not working very much and very, very few people working 60 hours per week. So this is a positively skewed distribution. All right, really quick, tell me what this one is. Yes, it is negative. And I'm not sure what this is a distribution of, but we could think about that. All right, so here's another nice picture showing the relationships between mean, median, and mode. I like to have this formula like in the back of my head. You're not responsible for knowing this, but basically, think about this. If the mean and the median are the same, mean minus median would be 0, right? And 3 times 0 is 0. So when skewness is 0, that means the mean and the median are the same. And think about this. If the mean is higher than the median, you're going to get a positive number up here. And a positive number times 3 divided by the standard deviation and all is going to give you a positive number. If the mean is lower than the median, this is going to give you a negative number. So it would produce a negative skew. Now, this is all going to be important later. That's why I'm going over this now. It's not the details of this equation that I want you to know, but I want you to know if something is skewed, if the mean is higher than the median, that it's positively skewed. And you need to know that. All right, so here's some more beautiful pictures to look at. Again, another way to look at it, you have very few extreme scores over here, but the median is more to the left. All right, I think we got that. If you want to practice this, maybe you're watching this with a friend and you want to do some fun, think about what a distribution would look like. Scores on an easy test with most scores scoring high and few students scoring low. What kind of distribution would that be? Maybe you want to play around with one of these. So check yourself, think about that. What would be some hypothetical means, modes, and medians? All right, let's continue to talk about distribution. Now we're going to talk about kurtosis. Now, if you just go around using these words, man, people are just going to think, wow, you're so smart. And really, it's these fancy words. I love it. I think leptokurtic is one of my favorite words now. Just say it, leptokurtic. Okay, so this has to do with the spread of scores. So if you remember, this bar right here is like the frequencies. So if we have a whole lot of people up here scoring at about the mean. So let's say this is IQ, and you have so many people scoring average IQ, but fewer people here on the tails. That's a leptokurtic distribution. Now, if the IQ distribution was like this, it's called platykurtic, kind of like a platypus bill. You know, it's flatter. So you have more of a spread of scores right here. And you have more kids up here in the high end, more kids down here in the low end, but there's more of a spread of scores here in the middle. There's more variability in the scores. Mesokurtic means that it is pretty normal. So when you look at kurtosis scores, when it's negative, it's considered a platic-kurtic score. If it's positive, it is more peaked. There are more scores closer to the mean. All right, so that's what that means. All right, we're going to talk about variability, range, interquartile range, variance, and standard deviation. Range, this is simple. It's just the difference between the highest number and the lowest number. All right, nothing tricky. 26 minus 19. What is that? 7. All right, now interquartile range. There 50% of scores are between quartile 1 and quartile 3. All right, so it's when we divide the data up and look at how 25% of the scores fall. Now remember what I said about the median? The median represents like everything below the median, 50% of scores fall. Everything above the median, 50% of scores fall. So if the median income is $50,000, and then the first quartile here maybe is $30,000. So anything less than $30,000 is in the bottom quartile of scores. All right, and let's say the higher quartile is 85,000. I'm totally making all of this up as well. Now, interquartile range is considered the range between quartile 3 and quartile 1. Now, how do you feel? To find quartile 2, which is the median, remember you're just finding the middle number, and the middle number is this 87. To find quartile 1, you find the median of this set, which would be 31. And to find quartile 3, you find the median of this set, which would be 119. So you will often see these box and whisker plots. Some of them are designed to show the spread of scores, like the whole minimum and maximum range. I'm going to tell you, JMP does not do it like this, but I just want you to be familiar. There are different ways to do box and whisker plots. So when you see a graph like this, this shows you that the majority of scores, well, not the majority, 50% of scores fall in this interquartile range of scores. And then there's a smaller range at the high end between quartile 3 and the maximum score. Now in JMP, you're going to see something that looks a little more like this, kind of, where these little whiskers here, it doesn't show you the full range of scores. It shows you an interquartile range where they do some math and they multiply the interquartile range by 1.5 and basically say that anything outside this interquartile range after multiplying it by 1.5 might be considered an outlier. That's like the gist that I want you to get here, that basically this helps us see that 50% of the scores are here. Here's where there's some other things going on, and here this is pretty extreme. I may need to calculate my analyses by including an outlier and also excluding it and seeing how it changes my results. Now ethically, if you take out an outlier, you have to report that, otherwise it's unethical. Let's talk about variance. I would like you coming in and I could say 1, 2, 3. Let's say the definition of variance is the average of the squared deviations from the mean. It's the average of the squared deviations from the mean. And so to calculate variance, I'm going to walk you through this again. Let's say that I have a number of ACT scores. These are the ACT scores here, okay? And so I need to find what is the mean of these ACT scores, and it's 20. So I'm going to subtract 20 from each one of these scores. All right, see how I did that there? And what do I get? I get -2, -1, 0, -1, -2. Did I do that right? No, 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 no. No, 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 no. These are positive numbers. These are positive numbers, okay? I don't want to redo this video, but please take note. Those are positive numbers. All right. So what should happen when you do this step? These should all add up to 0. Whenever you find the mean of something, when you subtract the mean from every score, it would always add up to 0. That is called the zero-sum theory. I can't believe I forgot to put positive signs there. Please do that. Okay. Now, what I would do is now I can't work with a 0. That doesn't really tell me how these scores here deviate from the mean. I want to know how different they are from the average. That's really what I'm doing here. So I square these numbers. And when I square these numbers, I get I get down here what this is called the sum of squares. Doesn't that make sense? It's literally the sum of the squares of the deviations. So right now I have the sum of the squares of these deviations from the mean right there. And to find the variance, what is variance again? It's the average of the squared deviations from the mean. So I take the average of this. And so I have 5 observations. So say 10 divided by 5 is 2. So that is the population variance. And then to find the standard deviation, I take the square root of variance and I get 1.4. And so going back here, doesn't it make sense now that I'm kind of finding how these differ from the mean? About how much do they differ from the mean? Well, the standard deviation, the standard kind of difference here is 1.4 from the mean. Isn't that neat? I'm hoping you see kind of what that standard deviation or difference is for those. Now, I want to say this. I want you to be able to calculate sample variance because in inferential statistics, we are working with making inferences from samples to populations. And so a more accurate way to say, hey, what the standard deviation is for the population from the sample is, I'm going to give a little more wiggle room in my numbers and in my math. And to do that, I am going to divide the sum of squares by n minus 1. So instead of dividing it by 5, I'm going to divide it by 4. And so that means my sample variance is now 2.5. And if I take the square root of that, the number will be a little bit bigger than 1.4. And it's going to give me a little more flexibility, a little more wiggle room in saying the standard deviation for this sample and representing the population is actually the square root of 2.5. All right, so this is what all of this looks like in a formula. It's like, oh my goodness, is this scary or what? It's really not. Look, sum of squares is the sum of the differences between the score minus the mean, square it, add them all up. That's what sum of squares means. Let's see here. That's a little too complicated. Sample variance. The whole thing that I just walked you through, this is what it looks like in a math equation. And remember, when we're dealing with samples, we're looking at regular plain old letters. We are not looking at Greek letters. So we have the score minus the mean, square them, add them all up. That's basically sum of squares. divided by how many observations there are minus 1. That gives me a little more wiggle room. That makes the variance a little bit bigger. All right, so what is variance? It is the average of the squared deviations from the mean. That's what it is. All right, remember, standard deviation is the square root of the variance. So we basically take what we had, take our answer here, and then take the square root of it. So this is what it looks like for the population variance, but what I want you to know is how to calculate it for the sample variance right here. All right. So another thing, as you read Hatcher, there's a lot on there about the distribution of scores. Really, the main thing I want you to know is that most scores fall between 1 standard deviation below the mean and above the mean. 68% of scores fall about here in a normal distribution. 95% of scores, let's say we're talking about IQ again, fall between 2 standard deviations above and below the mean. Then you get into some like not very many people have super high scores and not many people have super low scores in a population. Okay, so that's the gist of a normal distribution. With variance, you get it's so hard to like explain. It seems kind of complicated, but if you sit down and you practice a few of these, practice them through the Hatcher book, it's really not that hard. It's just very easy, simple mathematical calculate. Okay, so I hope to see you soon. Let me know if you have any questions. Thanks.